Looking at momentum, but now looking at it in terms of 2 dimensions. I'll give you an example to work with. So let's say this object is just, I don't know, doesn't matter what the hell it is. It's an object, right? And inside the object is a small explosive, or maybe a spring, or something, whatever. But something that is going to force the object apart into pieces. Now, if this is the before situation, what is its momentum before anything happens? 0. This is basically like the me and Shaq problem, right? If we're just standing there, the momentum is 0. So momentum initial is 0. Kilogram meters per second. Now, to compare, if this was a really simple one-dimensional momentum problem, don't write this down, all right? But if this was a really simple one-dimensional momentum problem, when the 2 objects exploded apart, they would, one would move one way, one would move the other in opposite directions. That's still one-dimensional, isn't it? This is just me and Shaq again, isn't it? Right? Or maybe one would go up and one would go down, but they would be in one dimension, up and down or left and right. That would be boring. That's not what we're doing. What we're doing is we're having this object move into distinct, well, into directions that are not one-dimensional. So, for example, one piece might go off with a momentum this way. One of them might go, let's say, this way. If there's 3 pieces, which way is the third one got to go? So would it make sense, for example, if the third piece went this way? All right, so conservation of momentum. What was the momentum before it blew apart? 0, right? So what do you think all 3 of these vectors, right, would need to add up to 0? Do those have any chance of adding up to 0? No, they're all roughly to the right, right? There's nothing. So I would expect my third piece to be, well, here, if I take these arrows to mean what I say, in other words, if this is the one vector and this is the other, in other words, the length of the arrow indicates the size of the momentum. There is a way, you might recall from the summer assignment that I'm sure everybody's done, is you can build yourself a parallelogram off of this. Does that look like a parallelogram to you? Rough, right? Yeah, not too bad. Maybe a little farther down. Then your third one, would it be in this direction? I'll make it in blue if I can get it to work. Here we go. Would it be in this direction? It'd be that size, but flipped the other way, right? Now, in this case, it looks like the stupid thing is, I didn't really mean it to be on the x-axis, but hey, what the heck? We'll just run with it. So these 3 vectors, the 2 red and this blue that I just did, we'll get rid of this one, they should add up to 0. Now, the issue is yeah, it is, that, for those of you who didn't hear that on the microphone, a student in my class just referred to this as a clock. It worked. It's really meant for the computer recording. It's not really meant for you to hear. See, when you watch the video, pardon me why I solved this tricky little problem. It's for the video. So when you play the video, my voice will be there. See, here in this room, I don't know how well it picks up. So we'll find out. Watch the video tonight. See if you hear yourself. If you were watching the video and you couldn't hear yourself, I'm really not talking to myself. I swear. Now, I am not going to... Well, we'll try it this way. So, let's make up some numbers, see if we can go through and look at this problem and how we might figure things out. But I will tell you this. We have to deal with x and y separately. Anytime you're dealing with vectors and you want to combine vectors, one of the first steps is to break them up into their components. So, assuming this is the situation and that this blue vector is in fact right along the negative x-axis, what would it look like, say for example, in the x dimension? All the x's in this problem add up to what? 0. Now, that's not going to be true in every problem. All right? If something was already moving, we'll look at some examples. If something was already moving, it would already have momentum. But in this case, the total is 0. What are the pieces that are going to make that up in the x dimension? Well, here. Let's name these things so it makes it easy. Let's call this object 1. So we'll make this momentum 1. Is this final or initial? Right? Because initial, everybody was stationary. So this is final. This is going to be, I'm officially going to change this one to green so that we can reference it. Yeah, you can draw this now. And we'll call the blue one, the object 3, its final momentum. And I guess I'll throw in some angles. So obviously the x is, this is right along the x. This is 50 degrees. Which, by the way, we'll call theta 1. And then this green one we'll call theta 2, its reference angle. And of course, theta 3 is, well, 180. We'll call it 0 degrees for reference. And we'll call theta 2 70 degrees. All right. So there's some information for us. So I haven't taken the time to assign exactly what these momenta are, and I got to be careful if I do, because I could assign them so they don't add up to 0. I'd have to go back, figure out what it is, but it doesn't matter. Because for us, what we're interested in is this. In the x dimension, what momenta are going to add up? So, for example, we'll start with all the ones going to the right. When I go to put in P1, do I write in, I do P1 final times what? X component. I don't want all of P1 final. I want its x component. And how do I find x components? If I have the reference angle, that's going to be the cosine of theta 1. Going in the same direction is the x component of momentum 2. So that's going to be plus momentum 2, final after the explosion, cosine of theta 2, assuming that theta 1 and theta 2 are, like this problem, reference angles. So I'm just worried about the x dimension. Right here. Going to the right. Do you agree with me that at least part of this red momentum vector is pointed to the right? Now the x component, I'm dotting that right here. That, how would I, because that's the only part pointing to the right. The other component is pointing up. I'll get to that later when I deal with the y dimension. I need to know how big this vector is. Well, x components, we take the magnitude of the actual vector, times the cosine of the reference angle. And we do the same thing for the green, correct? And we make them both positive because they're both going to the right. I'm almost done in the x. What's my last thing in the x? All right, this guy here is going to the left, so I'm going to put a minus on it. That's going to be minus P3 final. Bingo, you're right. And then, no, not worried about because it's all in the x. There's no y. You could use cosine of 0 degrees, but cosine of 0 is just 1. And so you're just going to have this anyway. All right, what about the y dimension? Could you write? So here's what you should do. If you're watching this at home, you should pause the video and then try this on your own, a similar expression. If you're in class, you should try to beat me here. You should work a little bit ahead of me. I will say this, that in this situation, I can't stress this enough, the initial momentum is 0. In fact, well, we'll just leave it like that for now. But it does not have to be 0. The total momentum does not always have to be 0, just because this object, in this case, started at rest. Momentum, the piece number 3, its momentum does not factor in to the y dimension because it's all on the x. So there's only 2 of them. Yeah, exactly. Your initial momentum will be the initial velocity times the initial, whatever the mass was. Right. Yes. Yep. Very good. So which one's, I would say this one's up, right? The red one's up. So you're right. I would go P1 final sine 50, sine theta 1, minus, because its y component for the green one is down, so minus P2 final sine theta 2. Yes, because these two are opposed to each other. Now, not every problem is going to have something breaking into 3 pieces. It might have 4. You could do this as many pieces as you want. In fact, this is the basic principle. If you've ever wondered, like when they investigate bombings or plane crashes or whatever, this is why they can start finding various pieces and reconstructing. If you've ever seen it, it's amazing how many pieces they find and they figure out where they go. You know that if a large piece went that way and a large piece went that way, that you're probably going to find one off in this direction. If you're watching this video, you have no idea what I'm talking about because I'm pointing. It's okay. So, but you get the you're not going to, if most of it's here, you're not going to expect more of it there. It's probably going to be on the opposite side of wherever location you are. So you have these 2 cases. Now, like I said, I'm not going to risk trying to solve this, make up numbers and solve it, because if I make up numbers and I make them wrong, it's just going to make this more confusing. Do we understand the general idea that we have to treat them separately? Okay. That we treat the x and y dimensions separately. We already know how to deal with vectors. It's December, all right? And it was part of the summer assignment, so hopefully we're good with vectors. All right. On to the next one.